welcome to the deep dive. Ever wondered what secrets are hidden inside those powerful microchips, the ones running your life, your phone, AI systems, all of it? They're just marvels of engineering, truly. But what happens when these tiny invisible flaws, things you absolutely cannot see, threaten their performance? How do you even find them? Well, that's our mission today. We're taking a deep dive into atomic force microscopy, or AFM. Now, okay, that might sound super technical, maybe like something stuck in a lab, but trust me, we're going to unpack how it really acts like a nano detective for semiconductors.
Yeah.
And it's absolutely vital for keeping all our tech reliable.
Precisely. And AFM's role in semiconductor failure analysis isn't just critical, it's really revolutionary. It's not just about getting a static picture, of a chip's surface. It's much more active. It's about probing and really understanding its electrical and thermal, let's call them secrets, at an incredibly small scale, atomic scale, really. We're talking details that are, literally invisible, even to many really powerful optical microscopes.
Right. So our deep dive today is going to explore how AFM goes way beyond just simple imaging. We'll show you how it reveals these crucial electrical and thermal insights, stuff that helps engineers diagnose and, maybe even more importantly, prevent major chip failures. We'll specifically look at modes that find those hot spots and weak links, the things that could otherwise just snowball into system-wide problems. Device failure. It's like detective work, but at the nanoscale. Fundamentally important stuff for the reliability of, well, all the tech you rely on daily, especially its electrical side. Okay, so let's unpack this a bit. AFM. You might know its basic job is imaging surfaces, right, with incredible precision. But what really elevates it, what makes it more than just a pretty picture, is its power to measure so much more than just height, just the topography. It's like a scientific Swiss Army knife.
Yeah, that's exactly where the true power lies for semiconductor work, these advanced modes. These capabilities let engineers get both things at once. The surface morphology, the shape and structure, and, crucially, local physical properties. Things like conductivity or temperature right there at the same spot. This dual capability is just indispensable. For failure analysis, sure, but also for really fine-tuning the manufacturing process itself. You're not just seeing what's there, but you're getting direct evidence, functional evidence of how it's behaving.
Makes sense.
So let's start with some key electrical modes. Think of conductive AFM, CAFM. You could call it detecting the tiny leaks.
Right.
How it works is it precisely measures the current flowing between a conductive probe, a tiny sharp tip, and the sample surface. This lets engineers analyze local conductivity, map out how current is distributed, even plot IV curves, that's current versus voltage at very specific points. It's perfect for finding those hidden leakage paths or maybe pinpointing defect locations in, say, an insulation layer, things that might otherwise go totally unnoticed.
Wow, okay. Like an electrical sniffer dog at the nanoscale.
Kind of, yeah. Then there's Kelvin probe force microscopy, KPFM. I like to think of this one as uncovering hidden charges. KPFM detects differences in surface potential, which relates to the work function of the material that's the energy needed to pull an electron off the surface. So this lets you see how electron energy levels are distributed and find these local charge traps, little pockets of charge. And that's critical because sometimes a chip can look physically perfect, absolutely fine, but it's electrically flawed because of these hidden charges messing with its performance.
Right, subtle problems that aren't about physical shape.
Exactly. We also have electrostatic force microscopy, or EFM. This one is maybe like mapping invisible electric fields. EFM detects electrostatic force. That lets you analyze how surface charge is distributed and also the dielectric constant of materials, their ability to store electrical energy. It's particularly useful for looking at things like charge injection or maybe local changes in the electric field within the device's, delicate structure. And for seeing the actual chemical recipe inside the chip, there's scanning capacitance microscopy, SCM. You can think of this as seeing the recipe, yeah, because it measures local changes in capacitance. This ability lets engineers map out doping distribution, that's the intentional impurities added to silicon and carrier concentration in semiconductors. Before SCM, figuring out the precise doping in a tiny transistor was, well, incredibly hard. Like trying to guess the ingredients of a complex soup just by tasting it. SCM literally lets you see the recipe at the atomic level. Huge for engineers.
That really paints a picture, seeing the ingredients.
Right. And finally, for electrical modes, let's mention scanning microwave impedance microscopy, or SMM. This one is truly remarkable. It offers non-destructive peaking at deep structures. See, before SMM, analyzing complex 3D things like FinFETs or 3D NAND memory often meant you had to destroy the chip layer by layer, slice and view.
Which is slow. You might destroy the evidence.
Exactly. Time-consuming, destructive, and you could easily hide the very defect you were looking for. SMM changed that. It gives you non-destructive analysis of nanoscale electrical resistance, capacitance, impedance. It's like giving engineers X-ray vision, allows for debugging in ways never possible before.
Incredible. And that's just the electrical side. What about heat? That's a huge issue in chips, too.
Oh, absolutely. So on the thermal side, we have crucial modes too. Scanning thermal microscopy, STHM, is about finding the heat signatures. It detects changes in heat conduction or just the local temperature between that probe and the sample. This allows for detailed analysis of heat transfer, finding local thermal defects, or pinpointing hotspots areas getting unusually warm, which could indicate an impending failure, overheating.
Finding the Seaver spots.
Precisely. And then there are the thermal expansion thermoelectric modes. These measure how materials expand when they get hot, or their thermoelectric effects, how they generate voltage due to temperature differences. This helps engineers detect thermal stress or perhaps material heterogeneity, subtle differences in composition. And those can also be root causes of critical failures, especially in high-power, high-performance chips.
It's really incredible when you think about it, combining the visual map topography with all this critical, unseen electrical and thermal information. And it's not just a picture anymore, it's like a full diagnostic report at the nanoscale, giving you the complete story of what's really happening inside. That must have been a massive leap forward.
Oh, absolutely. Transformative. The ability to correlate a physical defect you see with an electrical or thermal anomaly right there in real time at that scale, it really changed failure analysis from, educated guesswork into precise detective work.
So with this amazing toolkit, where do engineers focus when they're hunting down those really tricky electrical issues? You mentioned a couple of techniques stand out for pinpointing weaknesses and testing reliability.
That's right. Let's delve a bit deeper into electrostatic force microscopy, EFM again. As we touched on, it works by detecting those subtle changes in electrostatic force, probe versus sample. Its applications are pretty broad, mapping local charge distribution, identifying changes in dielectric constant, detecting electron traps, localized leakage paths. But what's crucial here is its specific suitability for analyzing those fundamental structures, like CMOS transistors, and pinpointing defects within the insulation layers. They are the backbone of, well, every modern chip.
Okay, so EFM maps the electrical landscape. What about putting things under pressure?
Right. That brings us to nano-TDDB. That stands for time-dependent dielectric breakdown. This is a direct reliability test. It really stresses the material. The idea here is you apply a gradually increasing voltage, a bias, using an AFM conductive probe, and you watch precisely when the insulating layer fails the breakdown voltage and how long it takes. This is just immensely valuable for testing the local strength of really critical components like the gate oxides in transistors or those low dielectric materials used for insulation. It can detect tiny, tiny pinholes or weaknesses in the dielectric that might otherwise just slip through. And what's truly revolutionary about nano-TDDB is its ability to analyze a single defect. You get much more specific, granular data compared to, say, traditional probe station tests, which just give you an average result over a much larger area.
I see. So it's like stress testing one tiny burr on a wall instead of just kicking the whole wall and seeing if it falls over.
That's a great analogy, yes.
So EFM gives you the surface electrical map, showing where potential problems might be lurking. And then nano-TDDB comes in to directly stress test the reliability, verifying those potential failure points. That combination sounds incredibly powerful. Do they ever tell different stories? Do you sometimes find an EFM signal where nano-TDDB shows it's actually okay or vice versa? How do engineers reconcile that?
That's an excellent point. Yes, that happens. Often, EFM might highlight an area with unusual charge buildup, suggesting a potential defect. But it doesn't necessarily tell you if that defect is critical, if it will cause a breakdown soon. So you can then use nano-TDDB precisely on that suspicious spot to directly assess its electrical strength and predict its lifetime. And yeah, sometimes you might find a strong EFM signal that doesn't lead to an immediate breakdown with nano-TDDB. Maybe it indicates a less severe issue, or maybe it's just a surface charge not related to a deep flaw. Or the other way around, maybe a spot looks okay with EFM but fails quickly under nano-TDDB stress. Reconciling those data points, that's really part of the art of failure analysis. It guides engineers to zero in on the most vulnerable, most likely to fail areas at the nanoscale.
Fascinating. Okay, let's talk about some of the biggest chip killers then. The really common critical reliability problems that plague modern chips. And how AFM acts as a defense. You know those moments maybe your phone suddenly freezes up or a brand new device just dies unexpectedly? Often the hidden culprit is one of these microscopic flaws we're talking about.
Indeed. One major villain is hot carrier effects, or HCE. This happens when carriers' electrons or holes inside a transistor get accelerated to very high energies. They get enough energy to actually jump into the gate oxide layer or get stuck at the interface. They're basically damaging the transistor from the inside out. When this happens, it can cause increased gate leakage current, make the threshold voltage drift, that's the voltage needed to turn the transistor on, and eventually the device degrades or just fails completely.
Like tiny energetic bullets damaging the core components.
That's a fair way to think about it. And AFM methods are incredibly effective at finding this HCE damage. For instance, CAFM, the conductive mode, can detect those local conductivity changes. It shows engineers where leakage or current spreading is happening because of these hot carriers. Meanwhile, KPFM, the Kelvin probe mode, can analyze surface potential changes. That helps find the precise location of trapped charges, the evidence left behind by the hot carriers. It lets us pinpoint the exact damage regions.
So if HCE is like this slow burn degrading the chip, AFM gives you the exact coordinates of that fire. How fast can engineers use that information, say, to tweak a new chip design? What's the turnaround like?
The speed is really a game changer. Once AFM identifies these problem areas, engineers can iterate really rapidly on their design or maybe the fabrication process. What used to take potentially weeks of destructive analysis, slicing and dicing, can sometimes be done in days or even hours in some cases now with AFM. It significantly speeds up development cycles and helps prevent widespread problems before chips go into mass production.
That's huge. Less guessing, faster fixes. What's another big chip killer?
Well, another critical one is electromigration, or EM. This is a different beast. It happens under very high current density. The metal atoms in the interconnects, the tiny wires connecting transistors, actually start to physically move, to migrate. This movement of atoms can lead to voids forming basically gaps where material is missing, or hillocks, which are bumps of excess material pushing out. Both of these, voids and hillocks, can eventually cause open circuits where the wire breaks, or short circuits where wires touch that shouldn't. Either way, it can kill the chip. Imagine like a microscopic road slowly eroding under heavy traffic until it just collapses.
Wow, the wires themselves rearranging. How does AFM catch that?
Well, AFM methods are invaluable here too. See AFM again. It can measure the local resistance along those metal lines. It can detect tiny fractures or voids before they become complete breaks, early warning. And just general morphology scans, looking at the surface shape with AFM, can detect those surface changes, finding the hillocks or cracks very early on, often before there are any electrical symptoms you could measure otherwise.
Okay, so this means AFM lets engineers find these EM potential areas before actual failure, which must significantly cut down risks in manufacturing, improve yields. It's like finding that weak spot in a bridge before it collapses so you can reinforce it proactively.
That's a perfect analogy, yes. And this really brings us to why AFM is so critical for tackling both HCE and EM. These are honestly among the most significant reliability challenges in modern nanometer scale devices. Everything is just so small and tightly packed. AFM gives you that sub-nanometer, sometimes down to atomic resolution, which means it enables the early detection of these critical danger zones, either during manufacturing R&D or in post-failure analysis. And this early detection is just indispensable for preventing widespread device failures and ensuring the robustness, the reliability of all our technology.
Absolutely crucial.
So, in conclusion, I think it's abundantly clear that atomic force microscopy is, well, it's far more than just a tool for scanning surfaces. Its diverse and advanced modes, electrical and thermal, make it a truly pivotal instrument in semiconductor failure analysis. It's capable of revealing these critical local changes. It allows us not just to see the surface, but to truly understand the potential failure mechanisms at the most fundamental level. And that really drives the reliability of the entire semiconductor industry forward.
And thinking about it, what does this all mean for you, the listener? Well, this kind of nanoscale detective work is absolutely vital. It's essential for managing the reliability of all the modern, advanced semiconductor processes. Without tools like AFM, honestly, engineers would be flying blind to a large extent, and the complex, powerful devices we all rely on daily, the phone in your pocket, the computer on your desk, the AI models that are shaping our future, they just wouldn't be nearly as reliable as they are today. So here's maybe a final thought to leave you with. As chips keep getting exponentially smaller, more complex, cramming billions, soon trillions, of transistors onto these tiny pieces of silicon, what new nano detectives might we need? What unforeseen challenges might emerge at these even smaller scales? And how will we continue to push the boundaries of what we can actually see and understand down there at the atomic level to ensure our technology keeps advancing reliably? It's this continuous quest for innovation, isn't it? Definitely something to think about until our next deep dive.